Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to be looking at some elementary topology, particularly the concept of the winding number of a curve around a point. And we're going to be seeing how the concept of signed area that we've been spending a lot of time on actually helps us set that up in a very concrete and computational way. So we're going to consider topology as arising from the continuum ultimately, which for us is modeled happily by the rational numbers. Real numbers are not necessary at all to do topology. But it's a particular property of the rational numbers that really brings this into focus. And that's the fact that there are positive numbers and there are negative numbers, and there's also zero. In other words, we can subdivide the rational numbers into three sort of types. The strictly positive ones, which are greater than zero, the strictly negative ones, which are less than zero, and zero itself. And each of these three types is naturally closed under addition. And moreover, each is closed under strictly positive scaling. And this is a quite pleasant property of this particular number system that's not so easily shared by other fields, for example, finite fields or the complex number fields. So it's a particular arithmetical property that has geometric or topological implications. Oftentimes it's preferable to restate that division into just two cases. The positive ones, which are x greater than or equal to 0, and the negative ones, which are x less than or equal to 0. In this case, these two types overlap exactly at the point x equals 0, which is from this point of view regarded both as positive and negative. And this is often more convenient, and in fact, generally I'm inclined to think in terms of these kinds of things with inequalities involving an equal sign possibility as well, instead of strict inequalities. I find that generally these are a little bit more amenable to things, but it's perhaps a matter of taste. Okay, so let's start talking about topology here, coming from the fact that we have positive numbers and negative numbers, particularly that we have positive numbers. So if we have 2 points A and B, then we can, I remind you, discuss the line segment AB and talk about a point C, say, being in this segment if it's written in this affine combination, 1 minus lambda A plus lambda B, where lambda is a number between 0 and 1. 0 here, all the way up to 1 here. Right? So recall this is the way we can describe points in a line segment. We can restate this by making it a little bit more symmetrical. We can introduce mu, another coefficient. So we have mu A plus lambda B, and now both of these coefficients are positive, and they sum to 1. So we're using the positivity here, the fact that we have positive coefficients, to be able to say what it means to be inside this interval. That's what positivity allows us to do. Happily, we can extend that one-dimensional notion of inside to a two-dimensional notion of inside. For example, if we have a triangle ABC in the plane, we can talk about a point D being inside the triangle, or maybe physically on the triangle. And okay, we might write D is on the triangle or in the triangle, and arithmetically it means that we can write it as an affine combination, mu A plus nu B plus lambda C, where these three constants are all positive again, and sum to 1. It's the two-dimensional analog of what we just talked about. And it describes points which are physically inside or on the triangle. Now I put a question mark here because this is maybe a little bit dubious notation, because strictly speaking our triangle ABC, if we actually look at its definition, it's a set of points. So this is not really such a happy notation, and it's probably preferable to make explicit the convex aspect of things by writing something like this. So we could write D is in the convex of ABC, the convex hull of the triangle ABC, is meaning this condition is satisfied. Okay, so that's a way of getting at the interior of triangles by, again, exploiting the fact that we have a notion of positivity. And of course, we have to remember, we have to have an affine combination where the coefficients sum to 1. Okay, so now we want to introduce an additional concept, the concept of being left or right of a particular directed line. Okay, so we'll start with an oriented edge AB. So this is a very simple kind of spline, a spline with just 2 points. And there's a first point and there's a second point. And with regard to that spline, we want to say whether other points are to the left or right of it. So here's a picture. Here's the point A. Here's a point B. There is the oriented edge AB in that direction. And we're then wanting to get at the fact that this half of the plane is to the left of AB, and this half is to the right. So how do we make that precise? How do we encode that algebraically so we can actually compute it? So here are the definitions. We'll say that a point C is left of AB precisely when the signed area of the cyclic-oriented polygonal spline ABC is greater than or equal to 0. And the cyclic-oriented polygonal spline ABC means that we're starting at A, we're going to B, then we're going to C, and then we're going back to A. So it's that cyclic thing. It's really the same as a triangle, except it's just slightly more general than a triangle in that the points are not necessarily having to be distinct. Okay, it's more general. But it's more or less equivalent to saying that the signed area of the oriented triangle ABC is greater than or equal to 0. So for example, this point here, this point D, if we look at this spline A, B, D, and then going back to there, so we're talking about that triangle there. Its orientation, we can see what it is a positive orientation. So we know when we compute the signed area of that, we're going to get something positive. That's telling us that D is to the left of AB. And we'll record that by saying that C is of type L of AB. L for left. And then the other side, C is right of AB when the same signed area, the spline ABC, cyclic spline, is less than or equal to 0. And we'll record that with an RAB. So this point E, for example, is going to be right of AB because if we take the spline ABE, that cyclic spline, calculate its signed area, we're going to get a negative number, as you can see, because it's oriented this way. Okay, the two cases overlap when the signed area is exactly equal to 0. In that case, we'll say that the point is aligned with AB. That's just telling us that we're actually on the line determined by the 2 points A and B. And notation C is in A of AB. So in this case here, this point D is in L of AB. This point E is in R of AB. This point F is in A of AB. This is aligned with AB. This is to the left. This is to the right. Okay, so now we're going to use the concepts of left and right to define when two oriented edges cross. Okay, so if this is an oriented edge and this is an oriented edge, then these ones don't cross. These ones don't cross. These ones don't cross. These ones do cross. These ones cross, etc. Okay, so two oriented edges, A, B, and C, D, cross. What's the definition? The definition is precisely when these two things both hold. When A and B are on opposite sides of CD, and when C and D are on opposite sides of AB. So A and B being on opposite sides of CD, what does that mean? It means that one of them is to the left of CD, and the other one is to the right. So maybe A is left and B is right, or maybe A is right and B is left. If either of those two cases occur, then A and B are on opposite sides of CD. So we want A and B to be on opposite sides of CD, and we want CD to be on opposite sides of AB. So for example, how about here? Here's AB, and here's CD, this direction. Okay, so if we look, are A and B on opposite sides of CD? So here's CD, and we look at that, and B is to the left, and A is to the right. And we don't really have to look at it. I mean, if these were actual points and we had their values, we could just compute signed areas of oriented triangles, and we'd be able to determine that. So A and B are on opposite sides of CD, and also if we look at it from the point of view of AB, then yes, C and D are on opposite sides. C is to the left and D is to the right. So these do cross. How about these two? This is a little bit more subtle because now AB is lying here with this endpoint exactly on CD. Okay, so let's think about that. So are A and B on opposite sides of CD? There's CD. Well, B is certainly to the right of CD. And what about A? Well, A is aligned with CD. That means it's both to the left and to the right. But in particular, it's to the left. So A is to the left and B is to the right. They are on opposite sides. Okay, we'll agree that's the convention. So, yes, they are on opposite sides. And are C and D on opposite sides? Well, yes, that's more obvious. There's A, B. D is to the left, C is to the right. So, yes, both conditions are satisfied, and these two oriented edges do cross. How about over here? Well, these don't cross. So one of these conditions is satisfied, but not the other. So it is true that C and D are on opposite sides of AB. So orient AB like this. Okay. Then if we're looking down in this direction, then C will be to the left and D will be to the right. So C and D are, yes, on opposite sides of AB. But if we look at it from the point of view of CD, both A and B are to the right of CD. They are not on opposite sides, so these ones don't cross. So I want to emphasize this is not primarily a pictorial thing when we're drawing pictures, but it's really something that if you had a computer program with thousands of edges and you wanted to know which ones are crossing, you could just go through them and calculate signed areas. And that's what you'd have to do. You'd go through, calculate lots of signed areas. So actually to calculate this, you really want to calculate 4 signed areas, right? So to calculate this first one, you have to calculate a signed area of CDA and then CDB and compare them. And over here, you have to calculate the signed area of ABC and ABD and compare them. Now let me remind you that a cyclic-oriented polygonal spline, or COPS, is a particular kind of spline that sort of wraps around where it started and which you can cyclically rotate. So here's typically what it looks like. So gamma is A1, A2 up to AN. These are all affine points with this double arrow on top. That denotes a COPS. And what it is officially is a list of points, exactly these points, but the list is enclosed in our pointy brackets, which is telling us that we are allowing ourselves to cyclically permute the elements of the list, and the list will not change. So we're able to take that A1 out and slot it to the end and shift everything over, and that's the same cyclic list. As lists, they're obviously different, but as cyclic lists, we agree that they're the same. So that's what a COPS is. Okay, now one of these COPS, like this one here, has oriented edges. So you just go through successive points, A1, A2, that's an oriented edge, A2, A3, that's an oriented edge. These are all in order, okay, up to AN minus 1 AN, and then the next one is the one that wraps around. AN to A1 is also an oriented edge. So the oriented edges themselves are organized. One is next to the other. One is adjacent to 2 other ones. Okay, so now we want to talk about when such COPS gamma is planar. And what that's going to mean is that there's going to be no non-trivial crossings. Okay, so gamma is planar precisely when no 2 of its oriented edges cross, unless they're adjacent. Unless they're adjacent. So for example, here is a COPS A, B, C, D, E, F, G. There it is there. And in this case, if you take any 2 oriented edges, say AB and DE, they do not cross. But adjacent ones do cross because AB and BC will cross because they have B in common. They have B in common. But other than that, there is no crossing oriented edges, so this is planar. This is planar. This one here is an example of something which is not planar. PQRS, that cyclic spline. PQRS, that should be an S. Let's change that. There we go. That thing is not planar. Why? Well, obviously because this oriented edge, QR, and this oriented edge, SP, they cross. So it's not planar. What about this one? It's a little bit more subtle. So oriented splines are rather flexible things, and we are allowing the points to do whatever they really want. So this is the spline L, M, N, O, P. So N and O happen to be the same, but we have a repeated vertex, okay. But still, in terms of oriented edges, this has oriented edge LM, as well as MN, as well as NO, as well as OP, as well as PL. And officially, this is not going to be planar because this edge MN and this edge OP, they're not adjacent. Like adjacent would be MN and NO. MN and OP are not adjacent. But if you actually look at them, there's MN and there's OP. They are crossing because they overlap at the point. Okay, so we have a notion now of planar, cyclic-oriented polygonal splines. This is a lot like a discrete version of a closed, simple curve, one that doesn't intersect each other. The kind of curve that topologists really like to study, even though actually saying what a closed continuous curve is very, very challenging, and I don't think it's really been done properly. Okay. But we're going to be able to avoid the difficulties in dealing with that level of sophistication and abstraction by just becoming much more precise in the finite situation and talking about these splines instead. And now we come to a famous and somewhat notoriously subtle theorem called the Jordan curve theorem, which we are here going to restate in a much simpler situation, call it the Jordan spline theorem. And it concerns a curve in the plane which is simple in the sense that it doesn't intersect itself. And the official theorem states that such a curve divides the plane into two pieces, two connected components, the inside and the outside. And this is a theorem which is often invoked, rarely ever proven. Okay, so because it's actually very hard to prove this, because if you're really going to prove it correctly, you have to get at the difficulties in the definition of what a continuous curve is. That's a very, very serious problem, which I talk about in my Math Foundation series. But here we're going to finesse that, go to this much more simple, discrete situation. So here is a spline. It's a cyclic-oriented polygonal spline, and our theorem is going to state that a planar COPS separates the plane into two connected components. And what does that mean? Well, it means there's an outside and an inside of this. First of all, let's check that this actually is a COPS. So let's start at some point here, okay, and let's go in the direction. So here we're going, boom. I'm just going to go through it very quickly just to convince you that there's no loose ends, so to speak. All right. Tracing it all the way, and we'll get back to where we started. It hasn't crossed anywhere. So the claim is that even though it may look rather complicated when you look at it from the inside, the outside going in, it's simpler. So from the outside, it's clear that this is outside and this is inside. So that's inside. So if I wanted to color the inside, well, I could kind of do it. I might just do a little bit. So the paint is going to flow. It's going to flow down here. There's a little bit gap there, so it can flow through. Over here, there, and then it'll flow through here to that corner. And we get over here, it also has to flow down here. Okay, so I've colored the inside of this COPS. And the theorem is that such a thing is always possible. We can always separate the plane if we have a COPS, which is planar. It has to be planar. If it's crossing, then it's much more complicated. And one way of thinking about the outside and the inside, or the difference between them, is that if you have a point outside, then this curve is not winding around that point. But if you have a point inside, say that one there, then the spline, even though it's doing all kinds of complicated things, is ultimately sort of winding its way around this thing exactly once. In this case, in which direction? I guess it's going in this direction. So I think it'll be going around in that direction altogether once. Okay, so a good way of thinking about this is to try to generalize and get at this notion of winding. A way of understanding this is to appreciate first the concept of winding number in greater generality when we let go of the planar restriction and just consider winding numbers of splines around points. So to understand winding numbers, let's first understand crossing number. So if we have two oriented edges AB and CD which are not aligned, in other words, AB is not aligned with CD and C and D are both not aligned with AB, then we're going to define the crossing number, C sub AB of CD. We can think of this as the crossing of CD over AB. Okay, this is going to be a number which is either 0, 1, or minus 1. It's going to be 0 if AB and CD do not cross. So if we have two things like this, they don't cross, the crossing number will be 0. Okay, but C sub AB of CD is going to be 1 if they do cross and C is to the right of AB and D is to the left of AB. In other words, we're doing things with respect to AB. If we're going from right to left as we cross AB, then that will be assigned a value of 1. So for example, here is AB, that oriented edge, and here is CD. And from the point of view of AB, which is the subscript, from the point of view of AB, C is to the right and D is to the left. So this edge CD is crossing over AB in the positive direction. If you think of counterclockwise as being the positive direction typically. So we're at A and we're watching this thing cross over, we're going in the direction B and it's crossing over, essentially in a kind of a counterclockwise direction. So that's going to be plus 1. And we get minus 1 if the opposite occurs, if they do cross, and now C is to the left of AB and D is to the right. So in this case, here's AB again, and now CD is crossing in the opposite direction. C is to the left, and it's going over to D on the right. So this is going to be crossing number of minus 1. All right, so now let me tell you about the winding number of a COPS, a spline, cyclic-oriented polygonal spline, around a point. So the COPS is gamma, the point is P. So for example here, in this case here, there's the COPS gamma, and P is a point. We can see in this case that it's inside, but okay, it doesn't have to be. And we can see that this COPS is going around it. It's going around it also more or less in a overall positive direction, this typically counterclockwise direction. So if you ignore this little wiggle here, then it more or less goes sequentially around to where it started, going around once. But we actually don't mind if it does a lot of wiggling. So we want to get at this number independent of how wiggly it is. In this example, we have gamma. This one is oriented in the opposite direction, and there's a point P in there. And in this case, the winding number is going to be minus 1 because it's going around once, but it's going around in the negative or the clockwise direction. If P was outside here, then both of the winding numbers would be 0. They don't actually go around P. In this case here, the spline gamma is a little bit more complicated. If we start, say, here, it goes here, and then here, and then here, 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 and back to where it started. And if that point P is inside there, then you can kind of see that as far as P is concerned, if P is watching this thing, you know, P maybe has to follow like this. He's watching it like this, and goes around once, and then he's watching it again. Maybe it goes back and forth, but he still ends up having to go around twice following it. So in this case, the winding number, gamma with respect to P, is 2. Now, this is not a course in topology, so I'm not going to present a whole theory here. I'm just going to give you the essential argument for an algorithm, which not only really defines this thing, but also allows you to calculate it. So the idea is that if P is trying to figure out what the winding number is, so one way is to like do what I just did and sort of follow it around, count how many times you go. But another way is just to not get dizzy and just to look in the same direction and just to record what the curve is doing. So if the curve is doing stuff like over here behind you, you don't care. You're only interested in what happens when it crosses the line of sight that you're looking at. Okay? So if it crosses in this direction, you're going to record a +1. And if it crosses in the other direction, you're going to record a -1. And that's all. Everything else, you're going to ignore. That's the basic idea. It's a very elegant idea. So here we illustrate that. Here's a point P. There's some complicated COPS gamma, closed, cyclic, oriented spline. And we've chosen a particular direction. So P happens to have chosen this direction. And the direction should be chosen so that none of the points of the spline are actually on here. Okay, so if you're looking in a direction, when you see a point exactly in the direction, just move the direction a little bit. Okay, so we're looking in this direction, and we're going to suppose that P is looking at a point Q, which is definitely outside the spline. So Q is far enough away that P is confident that the spline is not going to get anywhere near Q. So if we took a box around the spline, then Q is outside the box. Okay, so that gives us then an oriented edge PQ, from P to this point outside Q. And what we're going to do is we're just going to, as I said, we're going to look at all the splines which cross this edge. Exactly this edge from here to there. Behind us, we don't care. Just the edges which are crossing in front of us. So the winding number of gamma with respect to P is, well, it's a sum over all the oriented edges in gamma. So officially we're summing over all the edges. But we're summing the crossing number of the oriented edge AI to AI plus 1 with respect to PQ. So, for example, in this case here, P is looking out here. There's this edge which crosses, there's this edge which crosses, and there's this edge which crosses. All the other ones don't. So P is just going to record the crossing numbers. So this edge here, okay, P is looking out that way, going from here to here, it's crossing in that direction, from right to left, so that's a +1. That crossing number for that particular oriented edge will be +1. How about this one here? From here to here. Well, P is looking from the right to the left. So this one also gets a +1. And what about this one here? Well, that's in the opposite direction because it's going from left to right. So there will be a -1 for that crossing number. So although there are many oriented edges, most of them contribute 0 because they have to cross in order to contribute. And then they're either going to contribute a +1 or a -1. And then the grand total will be the winding number. In this case, the winding number will be +1 + 1 - 1 equals +1. This curve winds once around P. So that's a very nice algorithm. It can be implemented reasonably well on a computer. And the essential tool that you need is you need to construct or calculate crossing numbers. And for that, ultimately, you need to compute signed areas. So the signed area concept is just what we need, just what the topologist needs to be able to encode this kind of computational geometry explicitly on the machines so we can just deal with oriented splines. It's a very powerful and pleasant technology. So there's much to learn. I'm Norman Wildberger. Thanks for listening.